Hello everyone. Today I will give you a presentation about what is the effective way for the prevention of thermal runaway related with lithium battery, such as the data center and also the BESS, that is the system storage system. What is the effective way to prevent these disasters? This topic is mainly about this. First, let's say that what is the risk related with a lithium battery? In the past 3 years, the data center, there is a rapid expansion. From this table, we can see that the construction of the data center, the rise rate is more than 50%. And why there is such big demand for the data center construction? Because the first one is the AI requirement. Nowadays, I think most of us is very familiar with AI. If there is not AI, our life will be changed. For me, in the past, if I want to get information from a website, I usually use Baidu. But nowadays, I use Doubao and also DeepSeek. This AI, they can give us thorough knowledge. Not only just get the information we needed, it can give us some more comprehensive knowledge and also can do some deep research about the knowledge. So that's why we like to use AI. And also the other part, like the self-driving cars, the smart system, the smart hospital, all of these are related with AI. For the AI, what is the basis? How can deep earth give us so many knowledge, so much knowledge? That's because there is a big data stored in the data center. This big data is very important for us to get this knowledge. For the development of AI, they need more and more big data to be stored. So that's the basic reason for the expansion of the data center. And another reason is that there is the policy support and also the capital investment, and also is related with the national security. Together with the data center. In the data center, there is usually a backup UPS. This UPS is for backup, just like when there's some power shut down, the UPS can just continue to work. The UPS is consisted of the lithium battery. With the expansion of the data center, there are a lot of disasters or fire or explosion related with the lithium battery, with the UPS caused by the lithium battery. I just listed several of these. There are a lot of not in this table. Let's just look at this one. In September this year, it happens in South Korea. It is such a serious accident that caused 647 government digital services shut down. We can imagine that maybe that day no government can work because the digital service just stopped. We can think that if we go to the bank, we need the digital system. If it cannot work, the bank must stop that day. And also the other one last year in USA, it caused the Aliyun and also the other bigger data center to affect their AI systems operation. So this one cannot be prevented with the expansion of the data center construction, but we cannot stop by the difficulties. We must find some way to solve this problem, to find some effective way to give the timely alarm. And also, together with the data center, the energy storage system in the past 3 years, it's also still in high rapid expansion, especially outside China. because in China, our lithium battery has been developed for almost 20 years. We have established a lot of BESS. In the past 3 years, the outside China market is exploring. So together with this, there are several tens of disasters caused by the thermal runaway. Most of them, the basic reason is thermal runaway. It accounts for more than 70% of these disasters. In China, every year, there is also several tens happened every year. And these are some typical ones in China, and these are the typical ones in South Korea. For the data center, the UPS, it uses the lithium battery. And for the energy storage system, it also uses the lithium battery. So is the lithium battery totally the same for these two applications? Or can we use the same sensor for this two application? The answer is no. Let's look at the difference between the BESS cabin and the data center. For the BESS is usually constructed at a very far place in the desert. Why? Because if there is some accident, the risk is the smallest. It will not affect the other places. It will not cause disaster to the human people living around it. And the cost, the construction cost is also very low. But for the data center, 80% of them is constructed in the city center or in the suburb because it has the requirement of maintenance every day. These are the difference. For the data center, the temperature, the humidity, and also the particle content in this house, it is usually controlled at a very good condition. That's the difference of the environment of the BESS and the data center. But for the battery cell, for the BESS, it is charge, discharge every day, many times. So we hope the battery cell to have excellent charge and discharge ability. But for the data center, it is the backup power. It means that we hope it to have high energy density, but we do not pay too much attention on the charge and discharge ability. That's the difference. And for the thermal runaway, for the BESS, we can at least accept the fact that if there is thermal runaway, according to the design of the station, one cabin and between another, there are enough distance. When one cabin has a fire, it cannot affect the other cabins. It will not affect neighbors. We can at least receive this fact. That means we can accept it get into fire. And of course, it is better to prevent it at the first stage. But as to the data center, this cannot be accepted because in the data center, the room is very crowded and the battery has high energy storage. If there is some small thermal runaway or there are some small fire, we hope that we can find the point and extinguish this fire at the earliest stage. Only by this can we protect the data center from big losses. So they are quite different. And also for the BESS, the cabin is full of silicon for the sealness. So for the gas sensor application in these two applications, for the sensors for the data center, we put more attention on its high precision and also the ability to stand high temperature and also the stability at room temperature. But for the sensors used for BESS, we hope the sensor has excellent anti-silicon poisoning ability, and the sensor has a high temperature, working temperature range. Especially, we hope it can reach 85 centigrade. So that's the difference. Even we use the sensor for the lithium battery. They are all for the prevention, the protection of lithium battery. That's because the slightly difference in the application, we need to modify the performance of the sensor. And also for the data center, we hope that we can detect the gas at the earliest stage, at the ppm level. Only by this can we prevent it getting into a serious disaster. And now, what is the core risk related with the lithium battery? The first one is the thermal runaway. What is runaway? Runaway, you cannot stop it. It can only run. So if we cannot prevent this at early stage, we can only wait it for the fire to burn out everything. And during this process, toxic flammable gas will be generated, will be very vital, will be very dangerous to the environment. And also if the disaster happens at the data center, it will cause the loss to the wells, to the data, and it cannot be counted. It's very serious. Because the lithium battery, it has been evolved for several generations. Every generation, it has a different inner component. And when there is thermal runaway, there will be different gases or different parameters generated. So our fire protection strategies must evolve to address a unique safety challenge. Only by this can we provide the effective protection. So what is the potential root causes for the thermal runaway on site? That is the improper design. Because just for the BESS, we require that there must be enough distance between two cabins. If there is not enough, when the design of the energy storage station, it will cause disasters. And also, we need a proper way, an effective way to prevent the disaster. If we choose the one that is not suitable for this vertical application, it is also called improper design. And also there is the manufacturing defects and also the incorrect installation on site, because we cannot require that everyone be installed properly. There is the risk or there is the possibility of installation. Also the incompatible components and operational factors, all of these can contribute to the lithium runaway, for the thermal runaway of the lithium battery. So we already see that we know there is the possibility of thermal runaway, and there are some ways that we can use to prevent this. Now, what we can do is just to find a suitable way to detect and to prevent. Just like if we think that maybe I have a fever, I just measure the temperature of myself. Or if we think that there's something wrong with my health, we just go to the hospital to do some survey. And this one, we all think that if we use some suitable method, we can prevent this. But we must notice that the thermal runaway, it is very difficult to be detected at the very early stage. Why? There is the internal factor and also the external factor. For the internal factor, at the early stage, the fault gas generated is at ppm level. It is very, very few, very, very little the gases generated. And the voltage fluctuant is less than 3%. the inner temperature change cannot cause significant outside temperature raise. So this is difficult to be detected at the early stage. The indicators is very, very weak. And also, when the chemical reaction continues within the battery, when it reaches a point, the reaction is suddenly fastened. It will give us a very narrow time gap to give alarm. By this point, it's difficult to prevent this. And also, if we want to install a sensor into the battery cell, it's impossible because the environment is too corrosive, which will make everything, there's nothing can survive in this battery cell for a long time. That's the internal part. And the external part, when the temperature within the battery it raises, there is a time gap of 8 minutes for the external temperature to be detected significant raise. So that is the golden 8 minutes for the prevention of this. And also, there is a lot of VOC and interference gases within the cabin or in the data center. This will, the fault gas, the ppm level fault gas will be mixed with the interfering gas, and it's very difficult for a gas sensor to give the effective and timely and accurate detection. And the internal factor mixed with the external factor, it makes that it's very difficult to detect thermal runaway at a very early stage. But we still need to do this thing because with the expansion of data center, of the BESS, there are more possibility of the disasters. So we must need to find a way to solve this problem, to give the effective detection. This is what I introduced, the chain reaction process of the thermal runaway. And since we want to find a factor to detect this, what can we use? What parameter will be changed during this process? The first one is that there will be gases generated, just as the former process shows. At first, there will be ethylene and carbon monoxide, and then hydrogen and carbon monoxide. There are the gases. In the UL standard and NFPA standard, and also the GB standard, there is the requirement of the gases to protect, to prevent the thermal runaway. If we can find a suitable sensor for this application, this sensor can really protect or prevent the thermal runaway at a very early stage. So it is suitable for the protection at early stage and can be applied for all the stations. The next one is sound. If we can find a suitable sensor, the sound detection, the sound factor is can give an earlier indication than the gases. Why? Because where does the sound comes from? For the battery cells, there is a pressure relief valves. Only when this valve opens can the gas comes out. So that means the valves open is the first stage. Only when the valve opens can the gas come out. So from this process, the sound is a little earlier than gas. When the valve opens, there will be some sound, but it is difficult to be used widely. Why? Because there are some battery cell without a valve. Without a valve, where can we get the sound? And even the same type of battery from the same manufacturer, the valve open sound may be quite different. And also, when the sensor is working on site, there are also a lot of interference voice, like the voice of the air conditioner, of the fans, of the airflow of the bird, of the other animals. All of this maybe influence the detection. So this one, maybe it still needs more data, big data, to support its application. And the next one is temperature. Temperature, since there is 8 minutes time gap, so it can be used at the middle stage. At this time, maybe it's difficult to prevent. And also there is the smoke sensor. Smoke sensor, where does the smoke comes from? When there is fire, smoke is generated. So the smoke sensor is not for alarm, it's for start of the fire suspension system. That means if the smoke sensor give alarm, you can start the fire suspension system immediately, just to suspension the fire, not to prevent the fire. So the smoke is for the very late stage of this process. Also the pressure and the deformation. These two, it does not have too much application because it is more suitable for a battery cell. There is only seriously thermal runaway can there be enough gas to cause the deformation or cause the pressure sensor to give enough signal to be detected. So among all of these methods, the gas is the most widely used and is the most effective way to be detected. So which gas should we use? From this, we can see at the first stage, between the temperature from 90 to 120, at this point, as EI layer decomposition, it causes ethylene and carbon monoxide. So that means if we detect ethylene and carbon monoxide, maybe we can give earlier alarm. But there is not a suitable sensor for this application, so this one is not be used. At the second stage, when the temperature reaches 120 centigrade, hydrogen and carbon monoxide is generated in a large quantity. So by detection this, we can prevent the thermal runaway at a very early stage. Between these two sensors, between these two gases, hydrogen, because it is the smallest molecule in the world, it can run very fast, so it can give an effective alarm at least 60 to 120 seconds earlier than the CO sensor. So that is why the UL standard and the NFPA standard, all the researchers and the manufacturers in the US, they focus on the hydrogen signal. These are the NFPA 855. This standard is about the construction and the maintenance of the energy storage system. It cited a lot of combustible gas detector standard and also the toxic gas detector standard. This one is the related part in NFPA 76. 76 is about the fire suspension system in the data center. It emphasizes the hydrogen. And also NFPA did a lot of work. They want to find a suitable way to protect the system. They cited the combustible gas, and they think that the catalytic combustible sensor used to detect the flammable gas, there are some shortcomings. It is not be suitable for this application. Thanks to the work of NFPA, it helps a lot of company, but it's also gave the idea of the off gas, because there's when they drafted this standard, there's no sensor expert in participate in this work. So they gave the idea of off gas. What is off gas? Off gas is also a very excellent idea. It refers to the electrolyte vapor. Electrolyte vapor can come after several minutes to several tens of minutes earlier than gas. So if we can find a suitable sensor to detect this, it can really give the earliest alarm. But just like the Earth is so crowded, we think that we can go to the moon to live there. But is it possible? There is no water on the moon. We cannot survive there. So that means that is the similar. Although the off-gas is a very good idea, but there is not a suitable sensor for the off-gas detection. Nowadays, the off-gas detector on the market, they usually use the MOX semiconductor sensor. This sensor is usually for the VOC gas. It has the serious shortcomings of zero drift, and also for the silicate poisoned by this, it will lose its function at site. So that's the basis, that's the background of this. With this background, we need to think that maybe hydrogen and carbon monoxide is the most suitable gases to be detected. A lot of work has been done related with these two gases. Now we need to think about whether the standard is suitable for this vertical application, and will the standard give us some extra risk, or whether our detectors installed on site can give the timely or effective, accurate alarm, or will it give us a lot of after-sales service on site? All of this we should take into consideration. Now let's go through the second part about the gas sensing technology. Since I have introduced the carbon monoxide several times in details, so today I just focus on the hydrogen sensor, because this presentation is normally about the detectors targeted for the market outside China. The UL and the NFPA standard, they focus on hydrogen. So I just focus on the hydrogen technology. There are 5 principles that can be used to detect hydrogen. In fact, 5 of these have been used on site. There are detectors working on these principles, be working on site. And also they give a lot of problems. Within these 5, these 2, we can think that they are sisters from one family, the fuel cell and the electrochemical sensor. And the catalytic combustion and the metal oxide, we can think that they are brothers from one family. And also in the middle, there is the thermal conductivity principle. Let's explain this in detail. For the fuel cell sensor, there are 2 electrodes, the working electrode, the counter electrode, with the solid electrolyte between them, just like a sandwich. When there is hydrogen, it just reacts at the working electrode, and the oxygen at the counter electrode. The current generated is detected by the outside external circuit. The intensity is proportional to the hydrogen concentration. So by this, we can detect hydrogen accurately. This technology is the oldest one in the world. It is suitable for the application that has the requirement of high precision and long life. Why? Because this precision, it has very low noise. Only when the noise is low and the signal-to-noise ratio is high enough can it detect the gas at a very high precision. And a lot of my customers ask me, your sensor is very small. How much catalyst is used on your electrode? If I do not power the sensor, whether I can prolong the lifetime of this sensor? When will the electrolyte or the catalyst will be used up? So they worry about this. but there's no problem with this. The catalyst is just the supply, a platform that to reduce the energy needed for the reaction. If without the catalyst, we need to leach the carbon monoxide or the hydrogen to let it to react with oxygen. But with the catalyst's help, it can react naturally by itself. The catalyst will not be consumed. And the electrolyte, it is just a bridge from the working electrode to the counter electrode. The proton generated at the working electrode just goes to the counter electrode through this bridge. So nothing is a consumption during this process. And when this sensor is assembled, it is working all the time, no matter whether you powered it on or not. If you powered it on, we only get the signal out. Even if we do not power it on, it is still working all the time. And this is the diagram of the electrochemical sensor. It also has the working electrode, the counter electrode, but it contains a reference electrode. Why it contains a reference electrode? Because in the past, the fuel cell sensor, it has the problem of polarization. What is polarization? There are two kinds of polarization. The first one is about the offset. If the sensor, there is no problem of the polarization, this sensor is offset, is nearest to 0. That means when the sensor is aged, the offset is near 0. But if the sensor is stored there, the reaction is taking place all the time, but there's no outside, no external circuit. There's no this part, only this one. The molecular is react here. The electron just collected at the counter electrode, which will cause the offset of that sensor to a very high level. When you power on the sensor, the offset will lowered from a very high level, but it just takes time. It takes about 1 or 2 hours. It will not damage the sensor, only needs some time. Another one is about the sensitivity or the output, the stability of the sensor. When there is a high concentration of target gas, if the sensor does not have the anti-polarization ability, the output cannot be stable. Just like the room temperature is 26, but it cannot be stable. It can be 20, it can be 10. With time, it changes all the time. It cannot give an accurate detection. So they use a reference electrode to solve this problem. Within this sensor, in this white tank, it is full of the liquid electrolyte, just like the lithium battery. It also uses the liquid electrolyte. The electrolyte will exchange with outside freely, which causes the lifetime is very short, only about 2 years, and the sensitivity drifts seriously. From the data set of the manufacturer or the supplier, they usually say that their sensitivity drift is about 2% per month. So when this sensor is applied to the industry safety field, it is required according to the GB standard. It should be taken back to the factory for recalibration once per year, because every factory, it has its own laboratory for the calibration. But if we use this sensor on site with the lithium battery, can we take it back from the desert for the calibration? It is impossible. This reason can explain why the CO detector installed in the Middle East, most of them, their sensitivity drift seriously. Only about 20 to 30% sensitivity has been remained, because in Middle East, the temperature is very high. When the temperature is high, the liquid electrolyte, its evaporation is very high, which will cause the sensitivity drift. So every phenomenon of the on-site detector, it has the technical basis. If we can learn or do the research about the principles earlier, and we can evaluate the sensors earlier, we can prevent a lot of problems on site. These are the history of these two sensors. Why we say that the fuel cell sensor is the elder sister? It is the oldest one. In 1839, Williams raised the theory, raised the principle of the fuel cell. And until 1956, when the Clark oxygen sensor get into the market, that is the first fuel cell sensor. That means for the fuel cell sensor, the first one is oxygen, and the second one is the alcohol sensor. The alcohol sensor is developed by a team in the Vienna University. This team is leader, is my partner now. His alcohol sensor now has more than 80% global market, and we work together for selective formaldehyde sensor for 10 years. So because our company focus on the fuel cell technology, and they focus on fuel cell technology, so we work together to improve the performance of some certain gases. And then when time goes to 1980s, there are some other gas sensor get into the market. With the fuel cell sensor, there are only two electrodes. The mirror electrode is between these two, and the reaction electrode is also with two. But for the electrochemical sensor, there are three electrodes and two circuits. The red line, it refers to the mirror electrode. They output the current difference between the working and the reference electrode, and the chemical reaction happens between the working and the counter. So that is called the three electrode true circuit. This sensor is only in 1950s is the theory be raised by the expert, and then in 1960s also by the Vienna University, they make a protocol of the electrochemical sensor, and then in 1970s it is a commercialization that it's a sensor coming into the market. And nowadays, they also do the miniature of the sensor and try to detect more gas with this technology. That's the history of these two principles. Now let's see how the fuel cell technology detects. This one is the carbon monoxide sensor. This is the working electrode, counter electrode, electrolyte. When there is a carbon monoxide arrives at the working electrode, it reacts here together with water to generate the hydrogen, to generate the protein. And the oxygen just reacts at the counter electrode. Then the protein just goes through the electrolyte to meet with oxygen to generate a water molecule. And by this, the reaction finished, and the protein just output from the external circuit. This is the whole detection principle of this sensor. And this one is the principle of how the chemical reaction happens with the electrochemical sensor. This is also when hydrogen comes here, it reacts at the working electrode and the oxygen at the counter electrode. Between these two, there is water generated, and it just output the current difference from the working to the reference. By this, we detect the concentration. This blue one is the liquid electrolyte within this sensor. So these are how they work. And both of these two technologies have been used in the lithium battery-related field, like the BESS or the data center. So how do they perform on site? In China, all of the CO sensor with the battery, with the BESS, we use the fuel cell technology. Why? Because when we choose the sensor for this vertical application, we have the requirement that the sensor must have a long time, as long as 10 years. We cannot accept that we need to make the maintenance of the sensor every once per 2 years. So at that time, they found that Figaro has a carbon monoxide sensor that has more than 10 years lifetime. So from that time on, the carbon monoxide, fuel cell carbon monoxide is used in the BESS system. But this sensor, Figaro's sensor, is targeted development for the residential and commercial carbon monoxide alarm. Why I need to say it's targeted for this application? Because different application has different pins. For the residential and commercial CO alarm application, the biggest interference is from alcohol or the VOC at home. But for the BESS, the most risk is from the silicon. How to make the sensor has the anti-silicon poison ability is the biggest challenge. So this sensor, when it's working on site, there's some failure related with the silicon poisoning. And also the carbon monoxide detector installed outside China, they use the electrochemical sensor. Why? Because if you want to install a detector in America, your detector must have UL certificate. At that moment, only the detector with electrochemical sensor, it has UL certificate. This detector, when it's working on site, it has two significant problems. The first one I just mentioned, when it's installed in Middle East, the sensitivity drifts significantly. It cannot stand for 2 or 3 years. It needs the maintenance very frequently. And also when it's stored at the early stage, there is a lot of fault alarm caused by the silicon. This, we can see it in the later part. But this does not mean that the electrochemical sensor with the UL certificate is not good. That's because this detector is targeted development also for the residential fire or the residential toxic gases detection, not for this application. When it is used in the residential or the commercial application, it is very excellent, this detector. So we must use a suitable sensor or suitable detector for a vertical application. Only by this can we get a satisfying result. As to the hydrogen sensor, in China market, we once used the semiconductive sensor, which has the problem of fault alarm and misalarm, and we abandoned it. And then the manufacturers, they use the combustible sensor, catalytic combustion sensor, also meet with the problem of shortcoming and is also abandoned. Now, most of the hydrogen sensor used in China is based on fuel cell technology. Also, we once used the electrochemical pre-sample tool on site and also meet with the problem together, similar to the carbon monoxide. So we now focus on the fuel cell technology. The hydrogen sensor, the fuel cell hydrogen sensor on site, now we did not receive the feedback or the after-sale service problem related with this sensor, but I said we did not receive. It doesn't mean that there is no, because the hydrogen sensor quantity used on site is fewer than carbon monoxide. Only when the quantity is big enough, maybe some problem can be happens. So this can explain why the detector installed in Middle East its sensitivity drifted significantly, because we can just think this bottle is the package of the sensor. There is the electrolyte. The electrolyte has a certain humidity. It can exchange with the outside freely. If the outside humidity is higher than the inner part, it will absorb water, absorb, and then the package will crack. The sensor will totally damaged. And if the outside humidity is lower than the inner part, the water will go out, go, and then there is a very little electrolyte leaves. The sensor will become dry and will die. The sensitivity will drift significantly. So every phenomenon on site, there is the serial basic. And except the for the RCA of the failure of the sensor, except the electrolyte, there is also the catalyst. The catalyst is dedicated, developed for the carbon monoxide or for hydrogen. When it meets with silicon, the molecule is very big. It sticks on the catalyst. The catalyst cannot decompose it totally, so it just stays at the catalyst, which will cause the catalyst to be silicon poisoned. That's the basis or the reason of this one. Not only the electrochemical sensor, but also the fuel cell sensor, they meet with the catalytic poison problem. But for the fuel cell sensor, it also has the problem of the electrolyte. The electrolyte, although it is solid, it needs a suitable humidity range for it to have a good performance. Now, this is a result. This is a summary of this true technology. This is the sister. The sister, it is automatic poisoning to zero, the offset. It has more than 10 years lifetime. It is widely used for the application with the requirement for high precision and long service life. And there's no need for the recalibration during the whole life. And this sensor is temperature. It's easy to reach as high as 70 centigrade or 85 centigrade. But turn to the electrochemical sensor, the younger sister. It needs to be recalibrated once per year. Its lifetime is usually around 2 years. Because it uses liquid electrolyte, it's difficult for the sensor to work at a temperature higher than 50 centigrade or lower than minus 20 centigrade. So that's the difference between these two technologies. Let's see some detailed data tested. This is the storage test of a fuel cell sensor at a different temperature. We just store the sensor at the corresponding environment and took them out time to time to test the sensitivity drift. That is the room temperature, the minus 40 centigrade and 55 centigrade, and also the 55 centigrade plus 90% relative humidity. We can see that this sensor, it has a very good stability. This is the corresponding test with the electrochemical sensor. The lower two picture shows that the sensitivity drift significantly. This is the phenomenon what is happened with the carbon monoxide detector in Middle East. If we prolong the time, it will continue to drift. So that's this reason. And by this, we detect the fuel cell sensor's anti-silicon poisoning ability. From this, we can see that after more than 40 days, the sensor is not affected by this silicon. How do we do this test? We seal the sensor with the silicon together, and we change the silicon from time to time, because after the silicon is aging, becomes solid, there is no vapor comes out. So we change it from time to time to keep it wet. By this, our sensor did not be affected by the silicon. There's no silicon poison problem. And this one is the anti-polarization ability of this true principle. Since the expert, they developed the electrochemical sensor, the basic reason is that they want to prevent the polarization problem of fuel cell. But when we expose the sensor to 1000 ppm hydrogen, the output cannot be stable. It becomes lower and lower. That means this sensor, it has the problem of polarization. The reference electrode did not solve this problem totally. And this is our sensor. We also exposed the sensor to 20,000 ppm hydrogen for 30 minutes. The output is very stable. It means that even without this reference electrode, our sensor has the excellent anti-polarization ability. So that means that we cannot say which performance or which parameter is the shortcoming of technology, because by the design of the sensor, everything can be changed. And then we test the selectivity of the two principles, the two sensors to all of these interference gases. We can see that the electrochemical sensor has a crazy response to alcohol and also to silicon. It is 100 times fuel cell sensor's output. So this can explain why the CO detector installed on site, it gave fault alarm, because the catalyst used for the electrochemical hydrogen sensor is the same with the carbon monoxide sensor. It is very crazy with the silicon. It thinks there are a lot of carbon monoxide in the environment. It gave alarm immediately, but they just mistaken the silicon as the hydrogen or as the carbon monoxide. So every phenomenon on site, it can be prevented or it can be discovered in our lab if we can know the sensor principle very carefully. And we also test the sensor's ability to low humidity according to UL 2075. It requires that the sensor, we should test the sensitivity drift after 168 hours at this low sensitivity. From this, we can say the fuel cell sensor, the sensitivity, the drift is negligible. And this one, the electrochemical sensor, is drift significantly. And also we test the fuel cell sensor response or its interference, its anti-poisoning ability to these materials, which is usually used during the PCBA manufacture. Only the PCB cleaner will have some effect to the fuel cell sensor. The others, it is free from the influence of these gases. So the above part is about the sisters, the fuel cell sensor and the electrochemical sensor. Now let's turn to the brothers, the semiconductive sensor and also the catalytic combustion sensor. Why we classify them as the brothers? Because both of these sensors, we need to heat them to a very high temperature for the sensor to work. But the difference is that both of them, there is a platinum wire to provide the heat needed. And this one, the semiconductive sensor, it is coated with semiconductive material, the porous material, with platinum or with some noble metal particles doped. When there is gas absorbed within the pores, the conductivity of this material will be changed. By detection the changeless, we can determine the concentration of the gases. And for the catalytic combustion sensor, there is also a platinum to provide the heat needed. It is also coated with catalytic material. Also, it is porous. When there are gas comes, it will burn at the pellister. It will cause the Houston bridge to lose its balance and the voltage will be generated. By detection days, we can measure the concentration. Both of these, they have a serious silicon poison problem in the UL standard, the EN standard, also the GB standard. If we want to measure to make a detector with a semiconductor or the catalytic combustion sensor, there is the requirement that we must test the anti-silicon poisoning ability of this sensor. So this one, the off-gas sensor working on site, it works on the principle of the semiconductive. That can explain why the problem of the off-gas detector on site is that it gave misalarm. What is misalarm? There are some cases that the off-gas detector cannot pass the test of some systems in China because when they just put the off-gas detector with a lot of silicon inside, after some time it just failed the sensor. It became silicon poisoned, so it cannot give response. That is this point. Even we think that there is no wet silicon because the silicon vapor only comes from the wet one, or when the temperature is raised, the solid one will evaporate vapors again. The sensor has also another serious problem of the offset drift. Why the offset drift so significantly? Because everything that can cause the conductivity change, it will generate a signal. When a bird flies from the sensor, the air flows and it will also cause the conductivity change. It will also be mistaken as some gases. So that's the reason. When the offset drift, the information, the calibration data is not valid enough, is not valid either. So at this moment, it gave the misalarm. And for the pellister, it's also, that is the hydrogen sensor, the hydrogen detector installed on site. It usually uses this technology. It also has the problem of silicon pellister. The lifetime is very short. So that's these problems. Now the history of this tool, the MOX sensor, it is generated in 1936. And in 1962, they used the noble metal doped semiconductive materials to improve the sensitivity. And in 1968, it became a commercialization. And the Figaro from Japan is top one in this field, is a talent. Their semiconductive sensor, when using to their target field, they have a very excellent performance. And for the catalytic combustion sensor, The principle is raised in 1923, and in 1959, at first they use a platinum wire to detect the temperature change of this platinum wire. And in 1958, they found that if we covered the platinum with some catalytic material, the sensor can be more stable. And in 1960s, we used the Houston bridge method, and then it became a commercialization product. Nemoto from Japan is top one in this field. Their sensor, if it is applied for their targeted field, it also has a very good performance. And both of these sensors, they have the problem or they have the risk of silicon poisoning. Is the silicon poisoning method or the phenomenon the same? No. For the semiconductive sensor, when there is a silicon comes, the silicon will absorb in the pores. And when hydrogen or other gases comes, there's no pore for them to be absorbed. So the conductivity will not be changed. By this, the sensor is poisoned. And for the combustion sensor, when there is silicon, the silicon just also absorbed on this polyester, on the porous material. But this sensor, the temperature is higher. It just decomposed the silicon vapor into silicon dioxide. What is silicon dioxide? It's stone. So all this polyester is covered with stone. When the flammable gas arrives, there's no catalyst for it to be detected. So by this, the sensor is also silicon poisoned. They are different. Now let's look at the selectivity of the MOX sensor. Because the MOX sensor, it detects the conductivity change. Everything that can cause the conductivity change, it can be detected by the semiconductive sensor. This sensor, it is very excellent. It is the number one in the VOC sensor for the residential application. But we can see that it has response to the CO, to the ethanol, and also to the hydrogen sulfide. Why it can be applied for the VOC detection in residential? Because the VOC, it is a range. All of the gases can be classified as VOC. We need a totally result of all these gases, not like this. We hope that it can give the target response to the liquid electrolyte vapor. But in fact, it detects also all the vapor, silicon vapor, the VOC vapor in the cabin. So it has poor selectivity. Also, this is tested, the off-gas detector is offset drift. Within certain days, its drift is more than 150 ppm. And this one is the silicon poison. When we put the sensor, pack the sensor together with the silicon for 48 hours, the sensitivity drift is more than 40%. But when the sensor is used on site, it needs to live together with the silicon for several months or several years. How can we prevent this from the silicon poison? It's impossible because this shortcoming inherent from its principle. And this is the silicon poisoning of the catalytic combustion sensor. It is very, very quickly. In the standard, we usually test the silicon poisoning, the exposure to silicon for 20 hours. It's much shorter. It has more serious problem with silicon than the MOX sensor. And this one is the natural drift, sensitivity drift of the sensor, because there is a platinum that is working at a very high temperature. All the platinum particles, the catalyst, all of them are working at a very high temperature, which will cause these particles to be aged or to be oxidized. If the particles is oxidized, it will lose its function, will cause the sensitivity drift. So that's this shortcomings or the problems of this two technology. All the off-gas detector and the hydrogen detector on site, all their phenomenon, their performance on site can be explained by the theory, by the principle. Now there is a very hot principle called thermal conductivity. Why I say it is very hot? Because there are some companies claimed they can detect hydrogen accurately as low as 100 ppm. They can detect hydrogen sulfide as low as 2 ppm. Is that really the truth? How does this thermal conductivity sensor work? It detects also there is a Houston bridge within this sensor. Every gas, it has a distinguished thermal conductivity coefficient. Just like for the hydrogen, hydrogen is very typical because it has a coefficient 10 times higher than the others, and then the water and the carbon dioxide and also the methane, every gas has a different conductivity coefficient. If there's only one gas or only two gas, it can perform very excellent to detect. But in the cabin, it is a mixture. There are a lot of gas. How can we distinguish hydrogen from the other gases? And please pay attention to water. Even if the relative humidity is very low as 10%, the molecular of water, it is very, very much times higher than the hydrogen. So this sensor, it has the serious problem of the humidity effective. It will be seriously affected by the humidity change. Let's first look at this picture. When I received this thermal conductive sensor, my colleague tested its response from 100 ppm to more than 20,000 ppm. This line is the thermal conductive. Its linearity is very good, and its response time is very fast. The output is also very stable. At this moment, we cannot get to sleep because we think that this sensor maybe that is the most suitable way for this application. But when I discussed this with some of my friends, they just say that don't worry, just test the influence of humidity. Then you can decide whether there's the need to worry or not. Because I'm the manufacturer of a fuel cell hydrogen sensor, I hope that my sensor, my technology is more suitable for this vertical application. And then I asked my colleague to test the humidity influence through this sensor. My colleague said test the response, the linearity of the sensor in an oven. She set the stable temperature and the stable humidity. Then she just opened the oven door. The humidity just exchange with the outside with the lab humidity, which caused this data. The output of the sensor is as high as 1,500 ppm. That means only the humidity exchange will give a response to more than 1,500 ppm hydrogen concentration. And then she tested another test. She tested the response of the sensor to wet nitrogen and dry nitrogen. And also she changed the temperature and changed the flow rate. By this, it can give more than 2,500 ppm response. So if we just change the humidity, the sensor will give nearly 3,000 ppm response. And for the BESS system, the UL standard and the NFPA standard requires that the detector can start the fire suspension system at the concentration of no higher than 10% LEL. What is the ppm level of 10% LEL? For hydrogen, it is 4,000 ppm. That means our sensor has an error just caused by the humidity. It has an error of almost 3,000. We use this sensor to control the system, the fire suspension system, at 4,000 ppm. Do you dare to do that? I can't, because there will be a lot of malfunction. And so there's this part. And for some manufacturers outside China, they claimed on their sensor has minus or positive 4,000 ppm error of this sensor. Even if we can do the humidity compensation, we must pay attention, we must notice that the humidity sensor is usually made of polymer. The polymer humidity sensor is easily be poisoned by the silicon. So even if you can use the AI, use the big data to make the humidity compensation, the humidity sensor itself will draw your leg back, and it will also give you some bad response of your thermoconductive sensor. If it is used for the data center, we hope that we can detect at the earliest stage when there's a ppm level gas generated. We hope that we can detect it. So how can the thermoconductive sensor finish this task? It's impossible. Now, I introduced these 5 principles in detail. My purpose is that I do not want to say that one principle is better than another. We can only say that every principle has its suitable application. Every vertical application, we need to find a more suitable principle. Only by this, we can get a satisfying result. So what is the requirement of the BESS or the data center system? First, it must have more than 10 years lifetime of the sensor. We can't go through the desert to change the sensor once every 2 years. And it can stand high temperature and low temperature from minus 40 to 85 centigrade. Why I raise the higher point at 85? Because a lot of data from site, it says that the temperature within the cabin, before the system is put into operation, the temperature can reach 80 centigrade. So the sensor can stand this high temperature. And then that is, the sensor must have the anti-silicon poisoned ability, because the sensor needs to live together with silicon for many years. If it is easily be poisoned by the silicon, I think it maybe when the system is put into service, the sensor is dead. It's dead from the very beginning. And also it can have a very accurate detection ability. So that's the requirement of the sensors used for this application. From this, in a summary, we can see that only the fuel cell sensor has the possibility to meet all these requirements. For the thermoconductivity sensor, cannot detect low concentration very accurately. And also for the catalytic combustion sensor, the silicon poison and the lifetime is drawback. And for the NDIR sensor, hydrogen does not have absorption for this principle. So there's no NDIR hydrogen sensor. And for the semiconductive sensor or the off-gas detector used on site, the lifetime and the offset drift, the silicon poisoning are the top 3 shortcomings of this sensor. And also for the electrochemical sensor or for the carbon monoxide detectors installed on site, the interference from silicon and also the working temperature range and also the lifetime of this sensor is the drawback of this theory. Now, I have talked about so much about the principle. ProSense, what is our solution for this application? Wow, we have so many UL recognized sensors. We have UL recognized the carbon monoxide sensor and UL recognized the hydrogen sensor. All of these sensors, they have the ability of anti-silicon poison, just like the data I showed before, and also some extra data below. And all of these sensors, they can be used in the temperature range from -40 to 85 centigrade. If you browse the UL website and the catalog of product IQ, you can check our datasheet. We have modified our datasheet in UL certificate in UL systems to 85 centigrade. And all of them have more than 10 years lifetime, have selectivity to the target gas. It is have very little interference from other gases. So that's our solution. Let's look at our hydrogen sensor. We tested at 85 centigrade and 85 centigrade plus 85% relative humidity for more than 40 days, according to the car for the sensors applied in car industry. And also, we tested the sensor's response to 60% LEL hydrogen for 30 minutes to check whether it has the problem of polarization. The output is very stable. And this one is the 42 days package of the sensor together with silicon. Our customer gave us the silicon concentration and specified silicon we tested with days. After this test, the sensor's sensitivity, the drift is negligible. So our sensor has the anti-silicon poison ability. And this one, our sensor in UL 2075 for flammable gas tested, there is a test that to flood the sensor with pure gas. In the past, our sensor cannot pass this test because when the concentration is very high, the sensor will be totally damaged, irreversible. But after some modification, some upgrade, our sensor now can pass this test. Even flood with pure hydrogen, it can give a very good response. All of these tests support our excellent performance. And these are the similar tests to carbon monoxide, high temperature, the detection limit of 5 ppm, and also the anti-silicon poison ability. For the hydrogen sensor, I forgot this, because if the sensor is used for the data center, we hope that it can give alarm at the earliest stage. So the detection limit of our sensor is 100 ppm. It means that our sensor has the detection range from 100 to 24,000 ppm. During this wide range, our sensor can give an excellent performance. Now, all of this about the technical. At the beginning, we said that whether the standard, because if you want to do business outside China, you must meet the standard of the local region. For the US standard or the NFPA standard is the basic one. Whether this standard now can meet the requirement or it is suitable for the energy storage system for the data center, I don't think so, because when there is a product, when we draft the standard, at this point, the product has not too much application on site. When there are a lot of experience from the on-site, we just need to modify the standard to match with this application. From the former part, we can see that the UL standard or the NFPA standard, it cannot cover the risk or it cannot give target performance requirement for the application in this field. Now, I visited the UL lab and have a discussion with the sensor expert in UL and also with the committee of UL 2075, because now ProSense is the committee member in this TC. We discussed that we should to modify, to upgrade the UL 2075 standard to give effective advice about this product. From the sensor point, I think that nowadays the UL standard requirement for the sensor is too easy. It only tests 1 year stability and the temperature, the humidity, even the oxygen concentration, the wind speed is controlled seriously. But when the sensor is used on site, we cannot give such an environment. So by this, I suggest we discussed that we need to do more tests to raise some requirement of the sensor. Just like the sensor for this application, it should have the anti-silicon poisoning ability. It should have wider working temperature range, and it should have long life. It should have good selectability. All of this is vital for the application on site. And also for the detector, except this one, the detector should have good EMC performance. There are some cases that the sensor works, the sensor survives, but the detector, they lost their connection with the system. The alarm cannot be sent out. So for the UL and NFPA standard, in the future, there will be an upgrade toward this direction. Also, there are some top 1 detector manufacturer in US. They are doing the relative test, and they are also discussed with the ULSE to modify this standard. And also, the NFPA, the requirement is almost the same. NFPA also did a lot of job about the process of thermal runaway. Why they focus on the hydrogen? Because they found that during this process, hydrogen is the most effective one. It can be detected as the earliest stage. So by this, they hope that if we only use one sensor, we must use a hydrogen sensor. By this, if we can focus on the most effective parameter, and if we can find the most suitable principle of the sensor, we can establish a very reliable detector. What is the value of this reliable detector? It is the primary fire and exploration protection mechanism, and by this there is the business opportunity. You can meet the laws and the standards requirement on site, and also there will be a lot of intelligent operations on site. When this is realized, the owner of the system, the manufacturer of the detector, and the manufacturer of the sensor manufacturer and the insurance system, all of this, they can be benefit from the reliable early warning system. But what can we do to establish a reliable warning system within our company? First, we must have a clear idea about the requirements of your vertical application. By this, you must choose the reliable, the most suitable sensor, and you must do the evaluation test in your company to check whether this sensor's performance or the detector's performance meet the requirement of the vertical application. I think if in the past, the CO detector on site or the off-gas detector on site, if we can did some evaluation test, the simulation test in factory for several months, we can find the problem. Maybe these products cannot be installed on site. And then we need to find a facility or to get the certificate, just like if we want to sell the product in US, we need to get the UL certificate. Because the facilities, they usually have a system method to evaluate the sensor from every point. If we evaluate it by ourselves, maybe some point cannot be tested, because in UL standard, there is a system method for the reliability test. And with all of these things, we can just be happy to sell our products to all over the world. So by this, that is the root of this one. Now the final part, a brief introduction of ProSense. Now ProSense is the sole sensor manufacturer who joined the UL 2075 committee, and also the sole manufacturer who joined the UL 2034 committee in China. We are also the sole committee member as a sensor manufacturer in UL 2201. So when we work together with the committee, we know that we can contribute to the upgrade of the standard. And we only have 4 sensors. Our target of our company is that once we develop a sensor, we hope that the sensor can have better performance than others. We can solve some pain point in a certain vertical application. We do not want to get the market by the price battle. It is the worst way. We want to win our customer with the technique, with our excellent performance, just like our formaldehyde sensor. In the past 9 years, only new customers come to join us, but we never lose one customer. We have more than 70% market share. Why? Because this sensor has the highest stability when it is being used together with air purifier. And we also have the UL recognized hydrogen sensor, carbon monoxide sensor, and also the hydrogen sulfide sensor for solid-state lithium battery. So we hope that we can focus on a certain field, focus on a certain sensor to make it the best in the world before we turn to the next one. So that's all about this presentation. Now that is the context of our company. If you are interested with our company or our product, please contact with us. Thank you.